So just as we have higher order derivatives of functions of one variable, we also have higher order partial derivatives. For example, given the function f, its partial derivative f sub x, we can take the derivative of f sub x with respect to x or with respect to y, which account for 2 of the 4 possible second order partial derivatives. So that is the second order partial derivative of f are the partial derivative of f sub x and f sub y. So that is technically what you do to find the second order partial derivatives, is that you take partial x of partial f partial x. This would give you something called partial square f partial x square. Or this is another notation to indicate that this is the second order partial derivatives of f with respect to x. Similarly, if you want to take partial x of partial f partial y, this is going to give you partial square f partial x partial y, or this is f sub x y. On the other hand, if you want to find the second order partial derivative of f with respect to y, you do partial y of partial f partial y, and this gives you partial square f partial y square. There is another notation for that, is f sub yy. Now you can also do partial y on partial f partial x, and this is going to give you partial square f partial y partial x. Or there's another notation for this, that is f sub yx. And this is the second order partial derivative of f with respect to x, and this is the second order partial derivative of f with respect to y. There is a 2 second order partial derivative, that is f sub xy and f sub yx. This is called the mixed partial derivatives. The difference between the function of one variable with function of 2 variables is that function of 2 variables, you have 4 different second order partial derivatives of f. Alright, so we're going to apply this formula to find the second order partial derivative of the following functions. So in example 6, we're going to consider this functions f of xy equal to 3x squared y minus 6x times y to the 4th. Before finding the second order partial derivatives, you need to find the first order partial derivative with respect to x and with respect to y. So that is, we're going to do partial f partial x. And again, when you do partial f partial x, you're going to treat y as a constant. And partial f partial x is going to give you 6xy minus 6y to the 4th. Again, y in this context is a constant. Now for partial f partial y, you're going to take the partial derivative of the function with respect to y. In this context, you're going to treat x as a constant. So the partial derivative of this term with respect to y is going to be just 3x squared. And the partial derivative of this term with respect to y is going to be negative 6x times 4 times y to the 3rd power. And you can simplify this result and you get 3x squared minus 24x times y to the 3rd power. Now we're going to move on to finding the second order partial derivatives of the functions. So remember, for second order partial derivatives, there are 4 of them. So the first one is partial square f partial x squared. That is, you're going to take partial x of partial f partial x, and this is going to be partial x of 6xy minus 6y to the 4th. Again, in this context of finding the partial derivative of a function with respect to x, you treat y as a constant. So therefore, this y is a constant, and y to the 4th is also the constant. Therefore, this term is going to be a constant. So when you take the partial derivative, you're going to get just 6 times y. Now for partial square f partial x partial y, you're going to take partial x of partial f partial y, or this is partial x of. So partial f partial y, you got it right here, that is 3x squared minus 24xy cubed. And again, in this context of finding the partial derivative of the function with respect to x, y is a constant. And therefore, you get this is going to be 6x, y cubed is a constant, and you get this is minus 24y cubed, because the derivative of x with respect to x is 1. Now next, we're going to do partial square f partial y squared. That is partial y of partial f partial y, for partial y of 3x squared minus 24xy cubed. In this context, x is a constant, and therefore the partial derivative of 3x squared with respect to y is 0. Minus 24 times x times 3y squared, or this is going to be negative 72xy squared. Now for the last second order partial derivative, you get partial square f, partial y, partial x, or this is partial y of partial f, partial x, or this is partial y of 6xy minus 6y to the fourth. And when you take this partial derivative with respect to y, x in this context is a constant. So therefore, you get this partial derivative of 6xy with respect to y is going to be 6x and minus 24y cubed. Now, when you take a look at the result of the second order partial derivatives, you can see that for the mixed partial derivatives, the results are the same. We're going to arrive at one theorem a little bit later that is called the Clairaut theorem to indicate that if a function is continuous on its domain, then the mixed partial derivative is going to be equal to one another. Now, in example 7, you want to calculate the second order partial derivative of the function f of xy equal to x cubed plus y squared times e to the x. So to get to second order partial derivatives, you need to derive the first order partial derivative. So that is partial f partial x is equal to partial x of x cubed plus y squared times e to the x. So this is going to give us 3x squared plus y squared times e to the x. Again, in this context, y is a constant, therefore y squared is also a constant. Now we're going to move on to finding partial f partial y. That is partial y of x cubed plus y squared times e to the x. In this context, x is constant, right? So therefore the derivative of x cubed with respect to y is going to be equal to 0 plus 2y times e to the x, or this is just 2y times e to the x. Now for the second order partial derivative, you're going to do partial square f partial x squared, or this is partial x of partial f partial x. And this is going to give you 3x squared plus y squared e to the x. Now you take the partial derivative of this function with respect to x, and you get 6x plus y squared times e to the x. And for the mixed partial derivative of partial square f partial x partial y, you're going to do partial x of partial f partial y, or this is partial x of 2y e to the x, and you can still get 2y times e to the x because y is a constant in this case, and the partial derivative of e to the x with respect to x is just e to the x. Next, you do partial square f partial y squared, or this is equivalent to doing partial y of partial f partial y, and that is partial y of 2y times e to the x, and you get this is going to be 2 times e to the x. Again, x in this context is a constant, therefore e to the x is a constant, and 2 times e to the x is a constant multiple of y, and you can pull that out of the derivative operations. And the derivative of y with respect to y is just 1, so that's why you get 2 times e to the x. And the last one in this case is the mixed partial derivative, so partial square f partial y partial x, or this is equal to partial y of partial f partial x. So this is partial y of 3x squared plus y squared times e to the x. And the derivative of 3x squared with respect to y is going to be 0 because x in this context is a constant. And x is a constant, therefore e to the x is also a constant. When you take the partial derivative of this term with respect to y, you get 2y times e to the x. Again, we notice from our calculations that the result of the mixed partial derivative are equal to one another. Okay, now this leads us to the theorem, which is the Clairaut theorem, that's indicate that the equality of the mixed partial derivative. So if you have the mixed partial derivative of fxy and fyx, right, so this is the subscript yx, are both continuous functions on the disk D, which is in the respective domain of the functions, then f of xy evaluate at the point a, b, and f of yx evaluate at a, b for all the point a, b in D. In other words, that the mixed partial derivatives are equal to one another if the mixed partial derivatives are continuous functions on the respective domain. Now we're going to continue verifying that conclusions of the Clairaut theorem that the mixed partial derivatives are equal to one another given some functions. Alright, so we're going to take the first order partial derivatives with respect to x and with respect to y, and then we're going to move on to doing the mixed partial derivatives only. We're going to skip partial square f partial x squared, and we're going to skip partial square f partial y squared. In this case, you have the function u, so you do partial u partial x, and that is equal to 4x cubed times y cubed minus 0, because in this context, y is a constant. and you do partial u, partial y, and you get 3x to the 4th y squared minus 4 times y cubed. In this context, you're going to fix x and you're going to take derivative with respect to y only. For the mixed partial derivative, you do partial square u, partial x, partial y, and you have partial x of partial u, partial y. That is partial x of 3x to the 4th times y squared minus 4 times y cubed. So in this context, y is a constant and you take the derivative with respect to x only. And you get 3 times 4 times x cubed times y squared minus 0 because the partial derivative of this constant with respect to x is equal to 0. And you simplify the result, you get 12x cubed times y squared. Moving on to the other mixed partial derivative, so partial square u, partial y, partial x. This is equal to partial y of partial u, partial x. Or this is equal to partial y of 4x cubed, y cubed. And this gives you 4 times x cubed times 3 times y squared. And if you simplify the result, you get 12x cubed times y squared. And we just verified that the mixed partial derivative of these functions are equal to one another. Moving on to example 9, it's getting a little bit complicated for this function when you verify the conclusions of Laurent's theorem because you need to apply chain rule for this function when you find the derivative. Alright, so first you want to find partial u, partial x, that is partial x of cosine of x squared y. So cosine is the outside function and x squared times y is the inside function. But when you take the derivative of the function with respect to x, y is a constant. Right. So you take the derivative of the outside function and you get this to be negative sine of x squared times y multiplied with partial derivative of the term x squared y with respect to x. So this is the derivative of the inside function. So you got negative sine of x squared y times 2xy. So that's just the first order partial derivative with respect to x. Now we're going to do partial u, partial y, or partial y of cosine of x squared y. This is equal to negative sine of x squared y times partial y of x squared y. Again, you need to apply chain rule for this function because you have the outside function of cosine and the inside function of x squared times y. But in this context, x is a constant. And you get this is negative sine of x squared y times x squared. We're going to move on to finding the mixed partial derivatives. You do partial square u, partial x, partial y, or this is partial x of partial u, partial y, and partial x of negative sine of x squared y times x squared. Alright, so this gets quite complicated because here you get a product rule, and this is with respect to x. So this is still a function. This is not a constant. So you have to apply product rule of derivative. Now, before I apply the product rule of derivative, what I'm going to do is I'm going to take negative sign out of the derivative operation, so I don't have to worry about the negative sign anymore. So negative of partial x of sine of x squared y times x squared. So this is the product. So for this derivative, you need to apply product rule of differentiation. And you get, remember, we still have a negative in front. So the derivative of the first function multiplied with the second, plus the first function multiplied with the derivative of the second function. So the derivative of the first function, sine of x squared y, you need to apply chain rule again. You get cosine of x squared y times the partial derivative of x squared y with respect to x times x squared, which is the second function, plus the first function multiply with the derivative of the second function. Okay. And then you simplify what you got here, and you get cosine of x squared y times the partial derivative of x squared y with respect to x, and this gives you 2xy times x squared plus sine of x squared y times the partial derivative of x squared with respect to x, that is 2x. So I'm going to simplify this by taking 2x as a common factor, and you get negative 2x times cosine of x squared y times x squared y plus sine of x squared y. Now I'm going to keep the result only and erase all the calculations in the middle. So for the order mixed partial derivative, partial square u, partial y, partial x. you do partial y of negative psi of x squared y times 2xy. When you take the derivative of the functions with respect to y, x is a constant, so I'm going to pull out 2x here because it's just a constant multiple together with the negative sign. So you can rewrite this as negative 2x times partial y of psi of x squared y times y. And you apply the product rule of differentiation for this function. Now you get negative 2x times partial derivative of the first function times the second plus the first function times the derivative of the second function. When you take the derivative of the first function, you need to apply chain rule, and you get this is cosine of x squared y times partial y of x squared y times y, which is the second function, plus this first function, sine of x squared times y, times the partial derivative of y with respect to y. And you get this negative 2x times cosine of x squared y, partial derivative of x squared times y with respect to y, you get x squared, and y, this y is coming from the second function, plus sine of x squared y times the partial derivative of y with respect to y, this is going to give you 1, and that is the answer. Now, if you compare the result of the two mixed partial derivative, you can see that they are equal to one another. So that's it for me for partial derivatives. Please let me know if you have any questions. Thank you.